Okay, let's unpack this. Have you ever really stopped to think about gravity? I mean, really think about it.
It's one of those things we take for granted, isn't it? Keeps our feet on the ground.
Exactly. But it's so much more intricate, more surprising than just a simple pull.
Absolutely.
Today, we're doing a deep dive, drawing on some brilliant discussions from the StarTalk series, with Neil deGrasse Tyson, Charles Lulu, that crew.
Great source material there. They really get into the weeds.
They do. And our mission today is to pull out the key nuggets, maybe some surprising facts, and help you gain a new, maybe profound understanding of gravity.
Get ready for some potential aha moments.
Definitely. We might shatter a few everyday assumptions along the way. So let's start with the basics. Most of us learn Newton's idea, gravity as a force, an invisible string pulling things together.
The classic image. Comfortable, intuitive.
But then Einstein rolls up with general relativity and just completely changes the game.
Right. He says it's not a force in the traditional sense.
So for someone listening who kind of gets that, what's the really crucial distinction beyond just saying force versus curve? What fundamentally shifts?
Well, the key thing, and Charles Liu really nails this in the StarTalk chat, is when that difference truly matters.
Okay.
On everyday scales, even, solar system scales, Newton's math and Einstein's math give you pretty much the same answers. They're functionally equivalent for most things.
Right. So launching rockets, predicting tides, Newton's good enough.
Precisely. But when you get into extreme environments, like near black holes or thinking about the Big Bang, the very early universe,
Okay.
then seeing gravity as the curvature of space-time isn't just like a different way of saying it. It becomes absolutely essential.
Essential for the models to actually work.
Exactly. The Newtonian force idea just breaks down Einstein's geometry, the idea that mass and energy literally warp space-time and objects follow those curves.
Mm-hmm.
That's what accurately describes reality in those extremes.
So the aha moment is realizing gravity isn't just something happening in space.
It's something space itself is doing. It's a distortion of the fabric of reality. Not a pull between objects, but a bending of the cosmic canvas they exist on.
That fundamentally changes how you picture the universe.
It really does. It's a profound shift in perspective.
Okay, speaking of shifting perspectives, let's talk about dark matter, this invisible stuff that seems to outweigh everything we can see.
The big cosmic mystery holds galaxies together, but what is it?
Well, the source material we looked at throws out a really provocative idea, almost science fiction, but grounded in theoretical physics.
Oh, I think I know where you're going with this.
Yeah,
The leaky gravity idea.
that's the one. Gets your head spinning, doesn't it? What if dark matter isn't some weird particle here?
But ordinary matter's somewhere else entirely. In another universe, maybe?
Exactly. Explain that leaking concept. How would that even work?
Well, the hypothesis hinges on the idea of extra dimensions. Higher dimensional space, sometimes called the bulk in string theory contexts.
Okay, sticking with you.
The idea is that gravity, unlike other forces, might not be confined to our three spatial dimensions plus time. It could potentially leak or spill over between parallel universes or branes existing in this higher dimensional space.
So the gravitational pull we measure, the pull we attribute to dark matter.
Could actually be the gravitational influence of ordinary matter stars, galaxies, whatever, in a nearby universe bleeding through into ours.
Wow, the StarTalk analogy was great for this.
Yeah, the two aquariums, right, side by side, and the water pressure, the gravity from one subtly affects the other through some hidden connection.
A hidden pipe between realities. That is a truly mind-bending alternative.
It is. Highly speculative, of course, but it's an attempt to explain the observed gravitational effects without needing a completely new type of undiscovered particle within our own universe.
It opens up fascinating possibilities about the structure of reality itself.
Absolutely. Makes you wonder what else might be subtly influencing our cosmos from elsewhere.
Okay, let's zoom back in. From potentially infinite universes down to the potentially smallest scale of gravity, the particle level.
Right, the standard model of particle physics.
We have photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. Each force has its carrier particle.
The fundamental messengers.
But gravity.
Oh.
It's the odd one out. We have this theoretical particle, the graviton, but
Yeah.
where is it? Why is it so darn elusive?
The hunt for the graviton. Yeah, that's a huge challenge. It hasn't been directly detected, and there are good reasons why.
Such as?
Well, theoretically, if it exists, it should be massless, like the photon and gluon. That's one thing. But the main issue is its interaction strength.
It doesn't interact much.
It interacts incredibly weakly with matter.
Hmm.
I mean, vastly weaker than any other force. The source used a great analogy.
The whisper in a thunderstorm.
Exactly. Trying to detect a single graviton's effect is like trying to hear that whisper during a hurricane. The background noise of other interactions, even just quantum fluctuations, completely swamps it.
So it could be raining gravitons all around us and we wouldn't know.
Pretty much. But, and this is important, we do have indirect evidence suggesting something like it should exist.
You mean gravitational waves? LIGO.
Precisely. Detecting those ripples in spacetime, which are essentially coordinated waves of gravitational energy, strongly implies that there's a quantum mediator. Those waves are what you'd expect if gravitons were real and behaving as theory predicts.
So the waves are like seeing the ripples on the pond, even if you can't see the individual water molecules or gravitons moving.
That's a decent way to put it. The detection of gravitational waves was a massive confirmation of general relativity, and it bolsters the case for a quantum theory of gravity needing something like a graviton. Finding it directly, though, that's another story.
It really makes you wonder if we'll ever build a detector sensitive enough.
It's a monumental task.
Yeah.
But physics thrives on those challenges.
Okay, sticking with particles and fundamental forces. This brings us to that deep connection between mass, energy, and quantum stuff. We all know, even C.A. Wood.
The world's most famous equation.
But how does that simple equation and the quantum world it connects to really mess with our everyday intuition about what mass actually is?
Well, EMC itself is profound, right? It tells you mass and energy are two sides of the same coin. They're interchangeable.
Yeah, a little mass equals a lot of energy.
A huge amount. But the quantum connection adds another layer of weirdness. It reveals that even things we think of as massless can carry significant energy and, crucially, can therefore exert gravitational influence.
Because gravity responds to energy, not just mass.
Exactly. According to general relativity, is the presence of mass and energy that curves spacetime. And quantum mechanics shows energy can be concentrated in weird ways.
The source had a striking example.
The photon and the baseball.
Yeah.
Under the right, admittedly extreme quantum conditions, a single photon, which has zero rest mass, could theoretically be imbued with enough energy to match the kinetic energy of a 90-mile-per-hour fastball.
A massless particle hitting like a baseball.
In terms of energy content, yes. And therefore, in terms of its gravitational effect, too. The aha here is that mass, as we intuitively understand it, like heft, substance, is just one form energy can take.
So energy itself is the more fundamental thing that warps spacetime.
You could certainly argue that. Mass is just concentrated energy. This implies that even seemingly empty space, which has vacuum energy according to quantum field theory, or these massless particles whizzing around, they all contribute to the overall gravitational picture.
It really blurs the lines, doesn't it? Our common sense categories of stuff versus energy just don't hold up at that fundamental level.
They really don't. It pushes you to think more abstractly about what constitutes substance in the universe.
And all this weirdness, this blurring of lines, it feeds into the biggest challenge in fundamental physics today, right?
Oh, absolutely. The grand unification quest.
Trying to marry those two pillars, general relativity for the big stuff, gravity, cosmology.
And quantum mechanics for the small stuff.
Mm-hmm.
Particles, forces, probabilities.
But they just don't play nice together currently. It's like they describe two different realities that somehow coexist. Physics having an identity crisis, maybe?
Yeah, you could call it that. Or meter a creative crisis.
Mm.
It's this tension, this incompatibility between our best theory of gravity and our best theory of everything else that drives so much theoretical work.
Because nature must have one set of rules, ultimately.
Yeah, that's the assumption, the hope. And it's in trying to bridge this gap that some truly wild, speculative ideas emerge. The StarTalk material touched on some really cool ones.
Like using quantum phenomena to interact with things governed by relativity.
Exactly. Things like exploring whether quantum tunneling particles popping through barriers they shouldn't cross, or quantum entanglement, that spooky action at a distance, could somehow operate across relativistic structures like black hole event horizons.
Could you, send a message through a black hole using entanglement?
Highly speculative. But people are asking those kinds of questions. It's about probing the limits where both theories have to apply, like inside black holes or at the moment of the Big Bang, to look for clues to a deeper theory.
And then there are even grander ideas.
Like the many worlds interpretation of quantum mechanics, or broader multiverse concepts. Some physicists wonder if phenomena we struggle to explain within our single universe, like maybe the value of dark energy, or even aspects of gravity itself, could be consequences of interactions between universes, or relics of quantum branching.
So gravity could be an echo from another reality in the multiverse.
Again, way out on the speculative edge. But these ideas arise naturally when you push current theories to their limits and try to resolve their conflicts. It's where physics gets incredibly exciting, even if experimental proof is still far off.
It's exploring the very nature of reality at its deepest level.
Precisely. Trying to find that unified description.
So, bringing some of this high-level theory back down to, well, slightly more observable cosmic events, what does all this mean when really massive things interact? The source mentioned frame dragging. What is that?
Ah, frame dragging. That's a fantastic consequence of general relativity. It's the idea that massive, rotating objects don't just curve space-time, they actually twist it around with them.
Twist space itself.
Yeah, think of space-time like honey or a thick syrup. If you just put a heavy ball bearing, a non-rotating mass in it, the honey curves down around it.
Okay, that's the standard curvature.
Right. But now spin that ball bearing. As it spins, it drags the honey around with it, creating a little whirlpool. That's frame dragging. Massive rotating objects like spinning black holes or neutron stars literally twist the fabric of space-time in their vicinity.
Wow, so nearby objects get dragged along.
Their paths are influenced, yes. Their inertial frames, what they perceive as rest or straight-line motion, are literally dragged by the rotating mass. The here is seeing how dynamic spacetime is. It's not just a passive background. It's an active medium being churned and twisted by mass and energy.
So what happens when two of these spinning giants, say two black holes, get close and are about to merge?
Now it gets really complex and energetic. You have two massive objects, likely spinning maybe even in different directions, each dragging spacetime around itself. As they spiral closer, these swirling regions of spacetime interact intensely.
Like two whirlpools colliding.
Sort of. If their spins are opposed, you can imagine the spacetime between them getting incredibly stressed, incredibly twisted. There's significant tension generated in the geometry itself.
And this leads to some wild speculative questions, right?
Definitely. The source material brought up some possibilities. Could this intense spacetime tension, this extreme frame dragging interaction during a merger, actually enhance something like Hawking radiation?
The slow evaporation of black holes.
Yeah. Could the merger squeeze out more radiation? Or, even more speculatively, could the energy density and stress become so high that it triggers something called vacuum decay?
Vacuum decay. What's that?
That's a theoretical catastrophe where the fundamental state of the vacuum energy of the universe itself might spontaneously shift to a lower, more stable energy state.
Like the universe suddenly changing its fundamental laws.
In a localized region, potentially expanding outwards. It's very sci-fi, based on particle physics models. But the extreme conditions in merging black holes are one place. Theorists look for environments where such exotic physics might just be possible. Highly likely, but theoretically conceivable.
Good grief. It just shows how extreme these environments are. And it all ties back to that core idea from Einstein.
That your frame of reference matters. Near a spinning black hole, with spacetime being dragged, your perception of motion, of time, is fundamentally altered compared to someone far away. Relativity dictates what you observe.
What an incredible tour. We've gone from Newton's apple to Einstein's curved spacetime.
To leaky gravity from other universes.
The hunt for the elusive graviton, that quantum particle of gravity.
The deep link between mass and energy at the quantum level.
And this grand quest to unify everything, QM and GR, leading to ideas about quantum tunneling through black holes and maybe even multiverses.
And finally, seeing how these ideas play out in the real universe with things like frame dragging and colliding black holes.
It really hammers home that science isn't about having all the answers. It's an ongoing process, right? Full of mysteries and just astonishing possibilities.
Couldn't agree more. The edge of knowledge is always the most exciting place to be. And maybe this leaves you, the listener, with something to chew on. How does it actually feel to think of gravity not just as a pull downwards, but as you following a curve in the shape of reality itself?
A curve dictated by all the mass and energy around you.
Exactly. And what if some of those unseen influences shaping those curves?
Yeah.
What if they're whispers from realities beyond our own? Does that change how you see your place in the cosmos?
Definitely food for thought. We really encourage you to keep exploring these frontiers. There's so much more out there.